In this video, I want to explain how to interpret an exponential growth or decay function. So if instead of being given an explanation of what is growing or decaying, what if you're just given a function itself? You could, just by looking at this, you could know whether it's a growth or decay function, and you could know whether it's continuous or discrete. You could know the starting value, and you could know the rate, okay? And it's important to understand first that exponential functions are typically a function of time. So time is usually the independent variable. And oftentimes we put the ending value on the left side instead of writing this, instead of writing this is equal to W of t, we instead write the ending value on the left side, and we will say the ending value is equal to the starting value times 1 plus r to the t power, okay? And so typically what you see at the very beginning, the function, the name of the function with the letter of t is the ending value, okay? So that's typically the ending value right there, okay? And then the number that you see at the very beginning, which we are calling P naught or P sub 0, is sometimes called A, okay? Sometimes it's called A, all right? But it is, what you see at the beginning there is usually the starting or initial value, okay? And then this we've called the growth factor. But what we want from this, what this really is right here, is it's 1 plus r, okay? And so what we can do is we can take this and set it equal to what it is, 1.13, and from this information we can find the rate of growth or decay. And the way we do that is we subtract 1 from both sides, and so in this case we get r is equal to 0.13, okay? And if we want to turn that into a percentage, we can then take our 0.13 and multiply it by 100, and we get 13%, okay? And so there's kind of a faster way to do this, and I'm going to show you that now. So when we look at this, at any growth or decay function, or at least really it's a discrete growth or decay, we have this 1.13. Whatever is inside the parentheses, just take that number, 1.13, subtract 1, which will be 0.13, okay? That'll equal r, and then we take that 0.13, multiply it by 100, and we get the percentage, 13%, okay? And then we have the time value. T, the T is just the time value, and usually it'll be a letter, it won't be a number, okay? So let's look at this one, okay? So here we have an E, and because it's E, we have a continuous, okay? So this is continuous because we have E, and the R is not negative, it's positive, therefore this is a growth. Okay, this is a growth, okay? And in this case, R is very clear. R is equal to 0.052. And so if we take the 0.052 and multiply it by 100, equals 5.2%, okay? And so this is the percentage growth rate, and R is 0.052. And then this is our ending value, h of t, and our initial value is 61, okay? So that's 61 right there. That's our initial or starting value, okay? So there's another example. Let's look at a couple of the decay function examples, okay? Suppose that we're told that some population, something, it's a population, it's a dollar value, an investment, or a drug dose or something like that, and let's say that it's changing like this. So we want to know, is this discrete or is it continuous? is it growth or is it decay? Well, there's no E, and therefore this must be discrete, okay? So this is discrete. And if we want to, so P of t, that's the ending value. The starting value is 140. And we can see that the number inside of the parentheses is less than 1. And so we'll take our 0.76, we'll subtract 1, and we will get negative 0.24. And that means that this must be a decay. This must be a decay function, okay? So this is discrete decay, all right? And if we want to know the percentage, we'll take this 0.24, and multiply it by 100, and we get 24%. And so this function right here is experiencing a 24% decay or shrinking rate, okay? And so this is discrete decay, starts at 100, starting value 140, and that means that P of t is going to be smaller than 140 because it's shrinking or decaying. Now let's look at this last one here. We can see that the rate is negative. There's a negative in front of it. That means this must be decay, and because it has E, it's continuous. So this is a continuous decay. And its starting value is 73, and its ending value is V of t, and our time value is right here. And now let's look at our rate, okay? Our rate, or our R, is going to be equal to negative 0.019. See, with continuous, we don't have to subtract from 1. Whatever you see here actually is the rate. So the rate is negative 0.019, okay? The negative meaning that it's decay, and the 0.019 meaning that that's the rate. Now, if we take the 0.019 and multiply it by 100, then we know that is 1.9%. So this is a 1.9% decay rate, okay? 1.9% decay rate. And that's how we interpret these exponential functions.